A visitor from another star system is about to make its closest approach to our sun, and what happens in that moment could confirm our greatest hopes or deepest fears. This isn't science fiction. On October 29th, an object designated 3I Atlas will hit its perihelion at a blistering 68 kilometers per second. This is the moment a single, tiny maneuver could prove it's not just a rock, but something under intelligent control. So, what is the one signal scientists are looking for? Let's explore this together. The critical moment. So why does this one date, October 29th, matter more than anything else? This is the moment of perihelion, the object's closest and fastest point in its journey past the sun. At this instant, the laws of physics offer the greatest possible advantage for any change in trajectory. If 3I Atlas is just a comet, it will follow a predictable path dictated by gravity. But if it's something more, this is the most fuel-efficient moment to fire an engine and alter its course. For years, astronomers like Avi Loeb of Harvard University have urged the scientific community to consider the possibility that interstellar objects could be technological, arguing that we must be open to extraordinary evidence. This perihelion pass is the first real test. Every telescope that can get a clear view will be watching as it emerges from the sun's glare, looking for the slightest deviation from its gravity-defined path. We have seen comets exhibit non-gravitational forces before, but those are from outgassing, and they are typically gentle and chaotic. A sharp, deliberate change right at perihelion would be a different beast entirely. This isn't just another flyby, it's a critical junction that could validate or dismiss years of speculation in a matter of days.
Goes 19 limitations.
As 3I Atlas neared the sun, some pointed to imagery from the GOES 19 satellite as a potential way to track it through the glare. Here's the reality check. GOES 19 is a geostationary weather satellite, a masterpiece of engineering designed for one primary purpose: monitoring Earth's weather and solar flares, not faint objects from other star systems. Its instruments, the Advanced Baseline Imager and Solar Ultraviolet Imager, are optimized for tracking storms, not spotting a magnitude 12 object against the brightest thing in our sky. As science communicator Dr. Phil Plett often explains, using the wrong tool for the job gives you flawed data. The satellite's sensors lack the sensitivity and resolution, or plate scale, needed for deep space astronomy. This is like trying to read a license plate from a mile away with a pair of reading glasses. To get meaningful data, you need a meticulous process of astrometric calibration, correcting for the satellite's motion and optical distortions against a catalog of known stars. This is incredibly difficult with an instrument not built for it. While the idea is clever, it's scientifically unsound and produces results that cannot be trusted for this kind of precise work.
Debunking the rumors.
With an event this significant, misinformation is spreading faster than the object itself. Social media is flooded with claims of secret engine burns, doctored images, and supposed proof of alien intent. However, the International Astronomical Union's Minor Planet Center, the official body for this, has stated there is no confirmed evidence of any anomalous activity from 3I Atlas. Experts like Dr. Matthew Holman, a former director of the Minor Planet Center, consistently emphasize that scientific conclusions must be based on reproducible data, not blurry videos. The process of confirming a trajectory change is rigorous, requiring raw, time-stamped data and an error analysis that accounts for everything from camera noise to cosmic rays. Most viral claims use artifacts, hot pixels, or simple projection errors. People are falling victim to confirmation bias, seeing what they want to believe in random noise. The scientific standard requires that any claim detection must be independently verified by multiple observers using different equipment, until the object re-emerges from behind the sun and professional observatories gather that new high-precision data. All talk, of course, changes, is pure speculation.
The Oberth effect.
What if I told you the sun's gravity well is the most powerful engine amplifier in the solar system? This isn't a theory, it's a fundamental principle of astronautics called the Oberth effect, first described by the physicist Hermann Oberth in 1927. Imagine you're pushing a child on a swing. You get the biggest result by pushing right as the swing reaches its fastest point at the bottom of its arc. The Oberth effect is the same idea, but on a cosmic scale. A spacecraft's engine provides a much greater change in energy when the craft is already moving at high speed. As 3I Atlas dives toward the sun, it accelerates, reaching its peak velocity at perihelion. Firing an engine at that precise moment maximizes the fuel's efficiency. Dr. Nikki Fox, the mission lead for NASA's Parker Solar Probe, has used this principle in reverse, using close passes to shed velocity and tighten the probe's orbit. A modest burn of just a few kilometers per second would be magnified enormously by the object's incredible speed, allowing it to radically alter its trajectory and escape velocity. For a natural comet, this is irrelevant, but for a hypothetical craft, perihelion is the single most logical and efficient moment to change its destination, saving immense amounts of propellant.
Astrometry math.
So how will scientists actually prove a maneuver has happened? It's not about seeing a flare, it's about the cold, hard math of astrometry. Astrometry is the science of measuring the precise positions of objects in the sky against a background of fixed stars. Every observation is time-stamped, calibrated, and checked for errors. The data is then compared to a predicted path, or ephemeris, calculated based on the laws of gravity. Missions like the European Space Agency's Gaia satellite have revolutionized this field. As Gaia project scientist Dr. Timo Prosti explains, Gaia has created an unprecedentedly precise 3D map of over 1 billion stars, providing the perfect reference frame for this kind of work. When 3I Atlas reappears, astronomers will use this star catalog to pinpoint its location with arc-second precision. They will plot its position inside an uncertainty envelope, a cone of possible locations. A natural object will stay within that cone, but a maneuvered object will demonstrably break out of it. It's a process that requires patience, as multiple observatories around the world must confirm the same deviation to rule out localized errors. This collaborative cross-checking is the bedrock of astronomical discovery.
Delta V detection.
What's the smallest nudge that would give away an intelligently controlled object? The key metric is called delta V, which simply means a change in velocity. For an object like 3I Atlas at perihelion, even a tiny delta V produces a huge, observable effect over time. Here's the breakdown. A burn of just 1 kilometer per second at its closest approach to the Sun would cause its position in the sky to diverge by about 20 arcseconds by the time it nears Jupiter's orbit in March 2026. For context, the planet Jupiter itself is about 40 arcseconds across. A larger 7 kilometer per second burn would shift its position by several arc minutes, a gap easily detectable by mid-sized observatories. Dr. Jill Tarter, a renowned astronomer and former director of the SETI Institute, has emphasized the need for a clear, unambiguous signal that cannot be explained by natural phenomena. A sustained delta V that pulls the object outside its uncertainty envelope, the margin of error in its predicted path, would be just such a signal. If 3I Atlas does fire an engine, it will leave a clear, measurable, and undeniable signature in the sky that multiple independent observatories could confirm.
Why skip Earth?
If this object is an intelligent probe, many people assume its destination must be Earth, but from a purely strategic standpoint, that makes almost no sense. Why would an advanced visitor ignore easier targets and head straight for the most complicated one? Earth has a deep gravity well, meaning it takes enormous energy to land, take off, or even enter orbit. Furthermore, as NASA's planetary defense officer Dr. Lindley N. Johnson can attest, our planet is under constant surveillance. We have a global network of military and scientific sensors designed to detect incoming objects. Any unexpected arrival would trigger an immediate planet-wide response, what some have called a planetary immune system. An intelligent probe wouldn't seek confrontation. It would seek resources and a safe place to operate without alerting the locals. It already passed Mars earlier this month with no sign of slowing down. A direct approach to Earth would be the strategic equivalent of announcing your arrival to a potentially hostile and unpredictable civilization. The logical move for a visitor isn't to knock on the front door of the most heavily defended house on the block, but to go somewhere quieter and less defended.
The Jupiter option.
If not Earth, then where? The answer may lie with the king of the solar system, Jupiter. After slingshotting around the Sun, the trajectory of 3I Atlas, whether natural or altered, will carry it toward a close encounter with the gas giant. On March 16, 2026, the object is projected to pass within 54 million kilometers of Jupiter. This is the next major checkpoint. For any intelligent mission, Jupiter and its system of over 90 moons represent a perfect logistical hub. It's a treasure trove of resources. far from the complications of inter-system politics. Planetary scientists like Dr. Heidi Hammel have spent decades studying this complex system, highlighting its potential for both scientific discovery and future resource utilization. Jupiter's immense gravity could be used for another assist to reach other targets, or more importantly, to perform a braking maneuver to enter into a stable orbit around Jupiter or one of its moons. This would be a clear, unambiguous sign of intent. If a maneuver happens at the Sun, the resulting trajectory will tell us if Jupiter is the intended destination.
Ganymede resources.
Let's focus on the crown jewel of the Jupiter system, Ganymede. What makes this moon so special? It's the largest moon in our solar system, even bigger than the planet Mercury, and it offers a unique combination of resources perfect for an advanced technological presence. As astrobiologists, like Dr. Kevin Hand at JPL have detailed, Ganymede is believed to have a massive subsurface ocean containing more water than all of Earth's oceans combined. That water ice on its surface can be easily harvested and converted into hydrogen and oxygen, rocket fuel. On top of that, Ganymede is the only moon known to have its own magnetic field, which offers vital protection from Jupiter's intense radiation belts. Its gravity is just a fraction of Earth's, making it easy to land and launch spacecraft. Its thick ice shell, potentially kilometers deep, also provides excellent shielding from micrometeorites and cosmic radiation, making it an ideal place to build a protected, long-term base. It's the perfect combination: a gas station, a radiation shield, and a low-gravity construction yard all in one place, an unmatched piece of real estate in the outer solar system.
Barnard's Starlink.
Could this object be a message from our nearest stellar neighbor? One of the most intriguing, though highly speculative details about 3I Atlas is its origin point in the sky. Its approach vector traces back to the general direction of Barnard's star, a red dwarf just 6 light-years away. Discovered by astronomer Edward Emerson Barnard in 1916, Barnard's star is one of the closest stars to our Sun. Now, let's be clear, this is not proof of anything. As exoplanet expert Dr. Sarah Seeger from MIT would note, tracing an object's path back over such vast timescales is fraught with uncertainty due to the proper motion of stars. At the object's speed, the journey would have taken tens of thousands of years, and in that time, Barnard's star has moved. The alignment could be a complete coincidence. The scientific consensus puts the probability of 3I Atlas being an artifact at less than 1 in 1,000. However, it's a coincidence that is too compelling for astronomers to ignore. It keeps the question alive. As the object re-emerges from the sun's glare in late November, telescopes will be ready. The upcoming observations will replace speculation with hard data. So here we are, at a rare observational threshold. On October 29th, 3I Atlas makes its closest pass to the Sun. The data we have so far shows a natural object following a predictable path, but physics tells us this is the single best moment for a controlled maneuver. When it re-emerges from the sun's glare in November, the world's telescopes will be waiting to see if its path has changed. A continued natural trajectory means it will head out of our solar system, but a sharp, unexplained turn toward Jupiter would change everything. What happens next will be measured, not imagined. Thanks for joining us on Space Facts. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the cosmos. Thanks for watching Stellar Tech.